Hi class. In section 9.5, we'll be solving trigonometric equations. So what we're going to do is we're going to isolate the trig function. So for example, number one, it asks us to find all possible solutions for this equation. So in order to solve this equation, we need to solve for theta. Notice that cosine theta is already isolated, so that's a good start. We gotta always start there. We always have to make sure that the cosine or the trig function is isolated. Once it's isolated, you're gonna look at the unit circle and find the two positions or the two angles in which cosine is equal to 1/2. So if you look at your unit circles, you will see that one angle is going to be pi over 3, and the other angle is going to be 5/3 pi. And that's because cosine is positive in quadrant 1 and quadrant 4. So you can draw the coordinate plane, and you'll see that cosine is 1/2 has a cosine has a value of 1/2 there and there. Quadrant 1 and quadrant 4. This is pi over 3, and this is 5/3 pi. However, because it says all possible exact values, we can always go around the circle as many times as you want and find coterminal angles. So you can go around the circle infinitely many times, or as many times as you'd like, to find a coterminal angle of pi over 3, and also you can do the same thing for 5/3 pi. Therefore, whenever it asks for all possible solutions, exact solutions, you have to add 2k pi to each solution. So that's what we're going to do here because they're asking for all possible solutions. So we're going to add 2 pi k or 2k pi, it doesn't really matter. I like to add 2 pi k, where k represents any integer. Okay, so those are all the solutions. That's how you represent all the solutions, because you can always add a coterminal. You can always find a coterminal angle that would also be a solution. Okay, let's move on to the next problem. So this one is very similar. However, look at the trig function. Sine is not isolated, so that's the first step. The other thing that you notice is that they're asking us to solve for the solutions on an interval. So that makes it a little different. You don't have to find all the coterminal angles because you only have to find the solutions that are between 0 and 2 pi. So that makes it a little easier. Okay, so let's solve this equation. So let's just rewrite the equation that we're given. Step number one is to isolate the trig function. In this case, we're isolating for sine. Subtract 1. Divide by 2. We end up with sine equals negative 1/2. Once you've isolated the trig function, now you want to look at your unit circles and determine what angles has a sine value of negative 1/2. So once again, you will see that there are two angles that have a sine value of negative 1/2, and those two angles lie in quadrants 3 and 4. Okay, and those two angles are going to be, if you look at your unit circles, 7/6 pi and 11/6 pi. But because they're asking for only the solutions on the interval 0 to 2 pi, you do not have to find all the coterminal angles. So the final solution is just those two angles. All right, and that does it for this problem. Let's move on to the next page. Okay, so some considerations that you will see are sometimes you're going to need to substitute or use reciprocal functions. In other words, you're going to rewrite reciprocals such as cosecant and secant and cotangent in terms of sine, cosine, or tangent to solve. And then other times, when it comes to tangent, you're not going to have to add 2 pi k. Instead, you're going to only add 1 pi k, and you will see why in just a sec. So let's continue with the next problem. First thing we need to do is isolate the trig function like we've been doing. So in this case, we're going to add 1 to both sides. Okay, 2 sine squared theta equals 1. Divide by 2. sine squared equals 1/2. And this time we have to take the square root of both sides to cancel out the square. So when that happens, remember, we do get a plus minus. The square root of 1 is 1. However, 2 is not a perfect square, so we have to write that as square root of 2. That doesn't look like a ratio that we recognize as a special ratio on the unit circle. However, if you rationalize the denominator, you will see that you actually do get a ratio that is recognizable as a special ratio on the unit circle. You end up with radical 2 over 2. Plus minus, of course. So that means we should expect a total of 4 solutions. And once again, notice that they only want the solutions on the interval from 0 to 2 pi. So that makes it a little easier because you only have to identify the angles within these 2 angles. So let's go ahead and draw our coordinate plane and sine. Let's consider the positive pi over 2 first. The positive radical 2 over 2. There are 2 angles that sine is equal to positive radical 2 over 2. And those 2 angles are here, pi over 4, and 3/4 pi. And then the negative ones would be quadrant 3 and quadrant 4. And that would be 5/4 pi and 7/4 pi. So those are going to be our final solutions. So remember, we're solving for theta. We're solving for the angle. So theta is going to equal to those 4 angles, pi fourths, 3/4 pi, 5/4 pi, and 7/4 pi. That does it for that problem. Okay, let's move along. So here's a tangent problem. And once again, you always have to careful because this time they're asking for all solutions. That means we are going to find all the coterminal solutions as well. Okay, step number 1, isolate the trig function, which is nice because it is already isolated for us. So we can just start, with solving for x. So on your unit circle, what you want to do is you want to find the angles that have a tangent value of radical 3. Okay, so let's draw the coordinate plane. If you look at your unit circles, we know that tangent is positive because this is a positive ratio in quadrants 1 and quadrant 3. So the 2 answers need to be in those 2 quadrants. So it turns out that it will be this angle here. You can verify for me, pi over 3, because if you look at the ratio, that's going to have a ratio of 1/2, comma, rad 3 over 2, coordinates. And if you do the division, remember tangent is y divided by x. Tangent, theta, is y over x. So if you divide the y coordinate by the x coordinate, well, that's the same thing as multiplying by the reciprocal. You will see that you do get radical 3, which is exactly what the ratio we're trying to find. So this is indeed the angle that satisfies this equation. The other angle, as we mentioned, is quadrant 3 because a negative divided by a negative is also going to be a positive, and it's going to be directly across. And that angle turns out to be 4/3 pi. If you look at your unit circles, and the coordinates are -1/2, negative radical 3 over 2. It's the same exact process, and because a negative divided by a negative is a positive, you're going to get the same value. So those are the 2 solutions. However, because they're asking for all solutions, you do have to remember to add 1 pi k in this case, because look at this. If this is your solution and you want to find an angle directly across, what you would have to do is add pi. So you don't have to add 2 pi anymore, because that would mean you'd have to do 2 separate equations, one for each of these solutions. But instead, you can do both at the same time with one single equation by instead of just adding 1 pi k, 1 pi k, 1 pi k, etc. So in this case, it's kind of a shortcut. You only have to list the smaller angle and add 1 pi k. And that takes care of the coterminal angles for both angles. And that only works for tangent because the tangent solutions are going to be always across from each other. Okay, let's move on to the next page. Okay, sometimes you're going to end up with the quadratic equation that is quadratic in form. What that means is that you can rewrite the equation to be a quadratic equation, such as this up here, and then you can either use factoring or the square root property or the quadratic formula in order to solve for it. All right. They also show you how to do a substitution, so that's going to make your life a little easier, you will see. And then they also give you the quadratic formula in case you don't recall it from algebra. Here it is. So let's look at the next problem. As you can see, it already has you can already tell that it's going to be quadratic because of the square term, and then you have a non-square term, and then you have a constant. So first things first, you should always make sure the equation is equal to 0 in these situations. All right, and now you have to do a substitution. They call it a u substitution up here. So let's just do the same thing. Let's do an x substitution. Since the argument is theta, we can use x. If the argument was x, then I would use u. So let's go ahead and use, whoops, that's not what I wanted to do. I wanted to do this. Let's let x equal cosine. Whatever the trig function is, that's what you let x equal. Then you can rewrite the equation in terms of x. So you're going to write the equation as 2x squared plus 3x minus 1 equals 0. All I did was I took this equation and I replaced cosine with x. And this is the quadratic equation. So at this point, you can try to factor. In some cases, you won't be able to factor. So that's why I kind of just recommend that you go straight to the quadratic formula. Unless you'd like to factor and you're good at it, then go ahead and try to factor it. But if it's not factorable, then you will have to fall back on the quadratic formula. So I'm just going to go straight to the quadratic formula because this one actually is not factorable. So let's list out what A is, which is 2, the leading coefficient. B is the coefficient for the x, and C is the constant. If you plug in the values into the quadratic formula, you will get the following. Careful with the double negative. You see a minus here and a negative here. That's going to turn this into a plus. So you're going to end up adding 8 because 4 times 2 times 1 is 8. Double negative makes plus. So this is going to be 9 plus 8, which is 17 over 4. Okay, so that's x. However, we are not trying to solve for x here. We're trying to solve for theta. Look at the original equation. Our goal is to solve for theta. So this is what I recommend that you do at this point. You want to separate the two solutions, the plus and the minus. So one solution would be x equals negative 3 plus radical 17 over 4. And then the other solution, just draw a line in between, is going to be x equals negative 3 minus radical 17 over 4. Then we got to go back to our original substitution and replace x back with cosine. So x becomes cosine. We're just replacing this. We're replacing the original substitution back to what we chose it to be, which in this case we chose x to be cosine theta. Same thing on this side, except this is a minus. So when it comes to these type of problems, you got to remember that both sine and cosine are within negative 1 and 1. That's a range. So you can't get a cosine or a sine value that is greater than 1 or less than negative 1. So what you should do in this case, use your calculator to see what this becomes in decimal form, and same with this. So I'm going to save you a little bit of time. On the calculator, I already did this, and this is what I got. I got cosine is approximately 0.28, which is within our range. So that one's okay. The other one, however, if you do this on the calculator, I forgot the theta, cosine theta is going to equal to negative 1.78. And as you can see, that is less than negative 1. So this one has no solution. This equation will have no solution because, remember, cosine cannot be less than negative 1 or greater than positive 1. The other equation, though, will have two solutions. Just like the other problems that we've done, cosine is positive in two quadrants. So let me draw those two quadrants for you. Cosine is positive in this quadrant and this quadrant, 1 and 4. So this equation has two solutions, one in quadrant 1 and one in quadrant 4, because this is a positive number, 0.28, which means that theta, there are two solutions. One of the angles is in quadrant 1 and the other is in quadrant 4. But look at the equation. They don't want approximations. What they say in the problem is they want the exact solutions. Exactly means you're not supposed to use your calculator. So the only reason I used my calculator was just to determine if this was in my range for cosine, and it turned out that this one was not and this one was. But now we can find the exact values. The exact values, well, to find the exact value, you just take the inverse. So here's your first exact value. I'll call this one, whoops, that's not what I wanted to do. This one we'll call theta 1. This one we'll call theta 2. There's two solutions. So theta 1 is simply the inverse cosine of that expression. Negative 3 plus the square root of 17 over 4. Angle 2, or solution 2, is you have to use reference angles. It's this angle that's in quadrant 4. So since the reference angle is theta 1, this is a reference angle. To find theta 2, you have to do 2 pi, because this is 2 pi, minus the reference angle. So that is it right there. It's going to be 2 pi minus the reference angle. Cosine inverse negative 3 plus rad 17 over 4. And that is it. Two solutions. One solution, two solutions. That's a tough problem because there's a lot of skills that are required to be able to complete a problem like that. You got to know how to do the quadratic formula. You got to recognize that cosine and sine must be within the range of negative 1 and positive 1. In this case, it was not, so this one did not have a solution. In this case, it was, which meant there were two solutions, one in quadrant 1, one in quadrant 2. You have to recognize that this is a reference angle, and in order to find angle 2, you have to do 2 pi minus the reference angle. And that's it right here. 1, 2 solutions. Okay, let's look at the next problem. Okay, as you can see, this one is very similar because there's a quadratic involved, but you can't have mixed-matched, or in most cases, you do not want mixed-matched trig functions. You want everything in terms of cosine or everything in terms of sine. So what we're going to have to do is convert sine squared. We're going to use one of the identities in order to rewrite that as cosine squared. So remember, the Pythagorean identity says sine squared plus cosine squared equals 1. We can subtract cosine squared to both sides, and that'll give us the identity that we need. Sine squared equals 1 minus cosine squared. So that's a really big identity that you should have memorized, all right, because it comes up a lot. And now we can do a substitution. So now the new equation is going to become, instead of sine squared, we can rewrite that as 1 minus cosine squared equals 2 cosine theta plus 2. And now we have a quadratic, an equation that's quadratic in form that we can rewrite. We don't want the leading coefficient to be a negative, so let's move all of these terms to the right side. So I'm going to move those over by subtracting 1 and adding cosine squared. That's going to give us 0 on the left side. On the right side, you have cosine squared theta plus 2 cosine plus 1 after you combine like terms. Okay. All right, now let's do our substitution like we did in the previous problem. Let x equal the trig function, which is cosine. Now we can write that equation in terms of x. 0 equals x squared plus 2x plus 1. In this case, you can factor. I can already see it. You may or may not be able to see it, but if not, you should review your factoring. This equation is going to factor into x plus 1 times x plus 1, which can also be written as x plus 1 to the second power. Okay. All right, solving for x, you just set that factor equal to 0, and if you solve, you will get x equals -1. However, just like before, we are not trying to solve for x, we are trying to solve for theta. So once again, recall what we're supposed to do at this point. Replace the original substitution back in for x, which is cosine. So cosine replaces the x here. So let's go back up here, say cosine theta is equal to -1. And that has one solution. If you look at your unit circle, you will see that cosine has a coordinate of -1 when theta is equal to pi. And since they only want the solutions that are on the interval from 0 to 2 pi, we do not need to find all the coterminal solutions. So that takes care of this problem. All right, last page. Okay. Sometimes you're going to use the Pythagorean identity, which is what we did in the previous problem. Sometimes you'll need the double angle formulas. Sometimes you'll use sum to product. Sometimes you'll use product to sum. It just depends on the problem. Let's look at the next example. In this case, you don't want double angle formulas mixed up with just single angle trig functions. You don't want double and single angles in the same equation. You want everything in terms of a single angle. So in this case, we're going to use this identity. It's a double angle formula. So let's substitute this in for cosine 2 theta. So this equation will become 1 minus 2 sine squared theta equals cosine theta. And similar to the previous problem, we don't want sine and cosines in the same equation. So we're going to use the same exact identity that we used last time. Let me rewrite it for you so you recall it. Sine squared theta is equal to 1 minus cosine squared theta. That's the identity that you should have memorized. Okay, so now we can rewrite this as 1 minus 2 parentheses, replacing sine squared with 1 minus cosine squared theta, and then the rest of the equation is equal to cosine theta. All right, and now as you can see, we have everything in terms of cosines. We no longer have sines and cosines mixed up. We do, however, have to distribute the -2. So let's distribute this -2. So the equation becomes 1 minus 2 plus 2 cosine squared theta equals cosine theta. Okay. All right. Combine like terms, and also let's bring over the cosine to the left side. Since you always need the equation equal to 0 whenever you have a quadratic equation. All right, and we can combine these two terms, they're like terms. So 1 take away 2 is -1. So now we have 2 cosine squared theta minus cosine theta minus 1 equals 0. Notice that I'm writing the square term first, followed by the non-square term, followed by the constant. That's the standard form. Okay, now we're going to go ahead and rewrite this in terms of x. So we'll do our substitution. Let x equal the trig function, as we've been doing. Let's go to the next column over here. Let's rewrite the equation in terms of an algebraic equation, so it becomes 2x squared minus x minus 1 equals 0. You can try to factor this, and I believe this one is factorable, but it's not as easy to recognize as the ones that have a leading coefficient of 1. So I'm just going to go ahead and apply the quadratic formula. And you have the choice of trying to factor or going straight to the quadratic formula. I'll leave that up to you. So if you solve this, you're going to get x equals negative 1, which is positive 1, plus minus negative 1 squared minus 4ac all over 2a. After simplifying, double negative once again underneath the square root. Notice that's the double negative. That's going to be plus, so it's going to be 1 plus 8, which is 9, all over 4. Because you end up with the perfect square under the square root, that means you're going to get this radical is going to disappear, which means that tells you, if this is a perfect square, that tells you that the equation was factorable. So that's how you know if an equation is factorable or not, is based on the b squared minus 4ac part. If it's a perfect square, then it is factorable. And in this case, you do get 3, because the square root of 9 is 3. And now we're going to end up with 2 possible solutions, right? The positive, the plus, and the minus give us 2 different solutions, so let's write those out. One of them is going to be x equals 1 plus 3 over 4 is 1. And the other solution is 1 minus 3 over 4 is negative a half. Okay, I'm just going to divide that into 2 separate columns. So once again, we have to go back, replace the x with our original substitution, which is cosine again. And that's how we get, all right, that's how we get the equations. Here we go. Cosine theta equals 1, and cosine theta equals negative 1/2. All right, these both have solutions in quadrant. All right, so if you look at your unit circle, this one's going to have a solution of theta, which is equal to 2 pi. Actually, it's equal to 0, right? 0 has a cosine value of 1. But since we're looking for all solutions, we have to add 2 pi k to that. And then this one has 2 solutions. One solution will be in quadrant 2, and the other one will have a solution in quadrant 3. And those 2 angles are going to be 2/3 pi and 4/3 pi. Okay, so let's write that out. 2/3 pi, I'll call that 1, and I'll call that 2. 4/3 pi, but we must add 2 pi k to each of those to find all solutions, including the coterminal ones. So there we go, and there we go. And that will do it for that problem. Okay, let's keep going down here. Okay. Okay, so for this problem, okay, in this type of situation, when you just have a single trig function, you don't need to use a double angle formula. You can just go straight to the unit circle. After you've isolated the trig function, which it already is, you can look for what angles have a cosine value of 1/2. And if you go to your unit circle, you will see that, cosine is positive 1/2 at pi over 3 and 5/3 pi. You can verify that on the unit circle. Okay, so what you're supposed to do is you take the argument. The argument is 2x this time. It's a double angle. So you take the argument 2x, and the first angle has a value of 1/2 at pi over 3, and the second one has a cosine value of 1/2 at 5/3 pi. However, In the cases of double angle or multiple angle functions, you do have to add the 2 pi k to both of them, even though they do give us an interval to work with. In these situations, though, you still have to do the 2 pi k because there's a multiple angle involved. And so now you have to solve for x for both of these. So let's solve for x by dividing by 2. When you divide a fraction by 2, you're really just multiplying the denominator by 2. Same thing with this one, divide by 2, multiply the denominator by 2, divide by 2. Okay, so the equations now become x equal pi over 6 plus pi k. And this one becomes x equals 5, 6 pi plus pi k. Okay, now we must choose values for k to see which angles are going to fall in this interval. Okay, so you always start with k equals 0, and then you do k equals 1, and then you do k equals 2, etc., until you exceed this interval 0 to 2 pi. So let's start with k equals to 0. That's the starting point. For k equal to 0, if you plug in 0 for k here and here, well, this whole term will just disappear, and this term will disappear. So you'll just be left with pi over 6 and 5, 6 pi. So those are, so far, our angles are pi over 6 and 5, 6 pi. All right, now let's find the value, the angles for k equal to 1. So when k is equal to 1, you plug in the 1 for k, you're going to have pi over 6 plus pi and 5, 6 pi plus pi. So let's do that work down here. So pi over 6 plus pi and 5, 6 pi plus pi. Well, you can easily change this to a common denominator by putting a 6 over 6. That's the same thing as pi. Same thing with this one. 6 over 6 is the same thing as pi. And now you will get the next two answers, which are 7, 6 pi and 11, 6 pi. Notice that both of those angles are still within this range, this interval. 7, 6 pi is in the interval, and 11, 6 pi is also in the interval. So we have to add those angles to our list of solutions. Okay, for the next value of k, we would try 2. But guess what's going to happen? If you plug in 2 for k, you're going to have 2 pi here. 2 pi plus anything is going to exceed 2 pi. So because this is 2 pi, anything more than 2 pi plus pi over 6 is definitely outside of this interval. And same thing with this one. If k is 2, 2 pi plus 5, 6 pi is more than 2 pi. So you don't even have to do 2. It's clearly not going to give us values that are in the interval from 0 to 2 pi. So that will do it. This problem had 1, 2, 3, 4 solutions, and that is the end of this section.